I'm grateful to have these people here with me. Thank you very much for being with us. So we're talking about software architecture evolution and what to expect, right? So we had a few questions in mind, right? So for example, about talking about this evolution, we're thinking on silver bullets, right? We're talking about Frederick Brooks' silver bullets. So maybe you could explain a little bit about this to us.
Could I? That's a great question. So the idea, Fred Brooks actually, he wrote a famous article called No Silver Bullet, Essence and Accidents of Software Engineering. What he was actually trying to say was, there is no magic solution to many of the problems that we see in software engineering, but there are two sorts of complexity. There's essential complexity, which is never going to go away. From my old world of financial trading, if you're trading highly complicated derivative products, you're going to have quite a complicated system. That's just life. And actually, the more domains that I see, I realize there are very few simple domains. A friend of mine a few years ago moved to a library systems company. How many of you got a degree in computing? And how many of you were asked to write a library system in the first year? And it was a really simple problem? It's one of our canonical examples. It turns out library systems are really, really complicated if you actually know anything about the domain. So I think most domains are complicated, but what Brooks was saying was there's also accidental complexity that we inflict on ourselves. We get things wrong, we use the wrong tool, we use things that we don't create good abstractions, we're careless about language and terminology. And his thesis was we could identify tools and methods that can eliminate the accidental complexity, but the essential complexity is never going to go away. So what he's saying was there isn't a silver bullet. There isn't one thing that's ever going to make software engineering easy.
I also equate the essential complexity to the underlying computer science complexity that we have to deal with. So in a distributed system, distributed consensus is an essentially hard problem. It's never going to go away. And so I think we always have to think about dealing with those underlying theoretical problems that underpin our systems as well.
So after this, have we seen a silver bullet in the last 10 to 15 years?
Well, I don't think there are any. But no, I don't think in the software architecture field we've seen any one thing that's fundamentally changed the field. I do observe that there are some quite proven, well thought out techniques and approaches that very, very few people seem to know about. So fundamentally building models is something. There was a lot of discussion yesterday in a workshop about this, but I think everyone at that workshop thinks that building models in some sense is a good thing. Whereas when I talk to a lot of software engineers, building models is not something they consciously think about. An example from the architecture field, which Len Bass has done a lot of work on, would be scenario-based architectural evaluation. It's a really simple approach, and yet I introduce it to people, and it's always a huge surprise that it exists, which surprises me. And in my subfield of building secure systems, the idea of threat modeling. Now, if you go to the security community, threat modeling is like security 101. It's just like, but everybody does it. Whereas when you go to talk to most people building systems in payments, for example, where security is really important, they may not even have heard of threat modeling. They're certainly not doing it. So I don't think there's a silver bullet, but I do think there are really quite robust and simple techniques that we could do a lot more to publicize.
Okay, thank you. So you were commenting on having some ideas and having some ways of working. And I was thinking, many good ideas seem good on paper, but it turned out to be the opposite.
Yeah, definitely. I've had quite a few of those myself. So I observe this a lot, more kind of in a parallel world to Ian's, is that if you go into the software architecture research world, there's an awful lot of ideas that look credible on paper, but actually don't work very well. Mind you, there's plenty of things I think we've created an industry that honestly, somebody thought them up for a conference, and we then tried to apply them, and they didn't work so well. There's even whole frameworks have been created. We found that didn't work so well. The key thing is, which I keep on saying this to researchers, is there's no point experimenting on a toy problem. And actually, I think a lot of us fall into that trap, is that a real problem is just a bit hard. So when you're thinking something out, I mean, Nick Rosansky and I, when we came up with our viewpoints and perspectives approach, we fell into this trap repeatedly of thinking something out on a relatively straightforward problem and then going applying it to our day jobs and suddenly realizing this doesn't work at all. For example, because a real system is 10 times the size of your toy problem, and as soon as you multiply anything by 10, you're in a totally different, or 100 or 1,000, you're in a totally different kind of space. So for example, maybe you get an explosion of relationships which people hadn't thought about before. So I think it's testing it on real problems, and as a discipline, compared to, say, civil engineering, we're really, really bad at publishing case studies that allow people to experiment with their problems. If you look at especially the academic literature, but even the books that perhaps even some of us have written, the examples are toy problems. And where would you go to find a really good example? Because no company will tell you how their stuff works, because it's secret, and it's a differentiator, so they don't want to tell you how it works. So we're quite short of good examples in many domains to actually go and practice on.
So I believe you have a lot of experience with legacy code. But
Yeah, I do.
so we cannot publish these case studies to the outside, but how can we learn a bit more and create internally these case studies for our own learning?
Yeah, it's pretty straightforward, and that's one thing I recommend quite often when I visit different organizations, is that, how can I say, one of the most persistent problems I run into when I'm visiting organizations is they want to go and rework something, move to a slightly different style, or use a different technology, stuff along those lines. And invariably, they tend to be things where you have to go and do the same type of thing about 5 or 10 times in the code base. So it comes back to basically finding something which isn't trivial, isn't the most difficult thing, and then having a couple of people work on it, and kind of prove it out, and then basically sort of like spread the information around the organization, right? And it's I think just the fact that that's actually a novel practice in most organizations is pretty useful. It helps people to highlight something and basically go and point out that when you want to go and do something, this is a path that's been taken before. So there's a lot that I end up doing with companies.
On the issue of things looking a good idea on paper, I think as an industry we're an interesting case study, because product vendors obviously have an interest in making their technology attractive, and to do this they often paper over the weaknesses of their underlying technologies and concentrate on the strengths. So not surprising, I guess, it's marketing. Give you some examples. When I was at the SEI, we did a study for a client on the capabilities of NoSQL databases, a variety of them. And we did it empirically. We built code and everything and ran tests, sort of thing I like doing. And we found out that one particular database, I won't name names, was pretty bad at handling high volume writes, because it actually locked tables when it did a write. So this wasn't good. Like the table in a distributed database, not a good thing to do when you're doing a write. So the write throughput was ridiculously low. So on the other end, we found a database that had incredible write throughput, like phenomenal, like staggeringly phenomenal. However, you lost data if you weren't careful, because of the way it did consistency across replicas with last writer wins approaches. So all of these things were kind of trade-offs that they don't tell you in the documentation. And you can adopt these technologies and get a long way downstream building your system, and then you're in for a surprise when you think, oh God, I've got to use this database in a completely immutable style now, otherwise I'm going to lose updates, which for most people isn't a good thing.
So you have a good point about marketing and vendors pushing their ideas and their technology. So how can we detect these not so good things early on?
Prototyping, proof of concept prototyping typically is the way we've done it with clients. We can throw together prototypes which test out the essential characteristics of an underlying framework, whether it's a database or a messaging system or whatever, in a week. it's not hard to do to write really simple drivers that actually test out these capabilities. And it gives you concrete feedback on the way the system behaves. If you're just looking at documentation and listening to marketing people while they buy you lunch and wine and things like that, it's great fun, but you often don't get the technology that you want in the end, because it doesn't do what they tell you it does. It kind of does, but not always exactly how you want it to happen. So building prototypes, I think, is essential.
Yeah, and I think one thing that really helps as well is I'm seeing a lot more of this now than I did maybe 20 years ago or something like that. Essentially, if you're choosing a particular technology, seeking other people in other companies that are using the same technology who aren't necessarily competitors, right? So if you're in a completely different line of business, usually nobody would really mind you sitting down and talking to somebody and actually betraying, advertising the fact that you're using a particular technology and exchanging experience about using it. I mean, direct competitors, that's an issue, but if you're in completely different businesses just using a piece of infrastructure technology, it's quite often easy to go and share across companies and say, hey, we're trying this out and we ran into these issues. And there's a lot of different ways that can happen informally these days.
So this looks connected to what was said before about going and finding somebody who has built a similar system, or in this case, a similar technology, and ask them pointed questions on how to do things and what happens after a certain point, etc. Do you agree?
Yeah, definitely.
So we had another topic for our conversation. We were talking about common principles here in architecture, and I was wondering, and we were wondering at the at Apiumhub, are we trending towards more common principles, or are we making them more specialized in terms of architecture?
It's interesting. It seems like there's a lot of knowledge that basically had been around, I guess, like 30, 40 years ago that people continually start to rediscover within the industry. One of the things I'm kind of fascinated by is that there's this reasoning process we use when we're designing that doesn't seem very explicit sometimes. And yeah, I don't know quite what else to say about that except that it could be a bit more explicit. How do we actually reason about how particular scenarios of how teams interact with the artifacts that they're creating and things like this? Quite often if you meet very experienced architects or developers, they have a good intuition for whether something's going to work or not, but they don't really have an easy way of articulating this. The patterns movement kind of drove us in this direction of going and trying to codify a lot of this knowledge, but I think there's another step which is about kind of understanding interactions of things at a design level such that we can go and really teach that more effectively. And I think it's just an interesting area, and I think it's really, feels to me like it's missing at this point.
I think there's some issues that are coming up because we're starting to build larger, more complex systems and deploying them on shared virtualized architectures like clouds. As Len alluded to, these things are inherently distributed systems, and there's a whole body of computer science theory that tells you how hard distributed systems are, basically because they can fail in unexpected ways. And I'm surprised how few people actually understand some of those underlying distributed systems principles and how they can get bitten by failures when they're not expecting them. You also always bump into people who think they're a lot easier to solve a problem by building it themselves. I don't want to use that messaging system, it's stupid. I'm going to build my own, mine's going to be great. And 3 months later, they've still not succeeded because they've got all sorts of weird edge case errors that they just can't solve. So I think that's an issue for education as we move to more complex microservice-based systems that we're deploying in clouds. Then we really need to be cognizant of the distributed systems distributed systems theory that underlies the systems.
On the point of being specific or general, I think it's again there's an analogy in the security community where there is a danger that some security people are very generic and they talk about injection problems, but they don't actually tell you what an injection problem looks like. And other people are very specific and they say, in Java 8, the XML parsers are set up incorrectly, here's what you need to do. And security engineers will tell you that both of those focus points are dangerous. So I think we were talking a little bit about this yesterday, and some of the speakers this morning, George in particular, was sort of hinting at this too. There is, I mean, one of the papers quoted was 85, and there's stuff way back into kind of decomposing systems into modules type knowledge, where there are some timeless things that apply in many, many places, but there's also, if you're going to build a microservice-based system on the Google Cloud using the following services, there are things you will need to know. So people need to be aware of both. I was kind of reminded that years ago I heard Michael Jackson, not the singer, not the beer guy, the other one, who was at a conference in the UK, and I'm not sure if he wrote this down, but he had a very wise thing he said was, he obviously worked in structured methods for many years when they were fashionable. And he said he was always very suspicious when he read a new book about a new structured method and they told you that it was applicable to everything. And he said what he always wanted to know was how narrowly applicable it was, because it could only possibly address the challenges of certain kinds of systems. So he was always much more interested in what doesn't it do. And I think sometimes that's maybe why we search for generality, because it's very seductive. But actually, we run into this problem that we end up with a whole lot of very generic principles that, yes, they're valuable, but without being specialized to a situation, they're quite dangerous.
So what I'm getting is that there are generic or general principles, but in our day-to-day, we should be more specific and more actionable, and we should be able and be comfortable moving in those two spaces.
Yeah, I think so. I think it's that a good architect can work in both. There is background generic knowledge, they've got all that. Len was referring to earlier about there's a lot of knowledge already known, but in your specific situation, you can't just apply it blindly.
It seems like the force that really kind of moves against that is like advocacy, right? So if you are basically an advocate of a particular approach, your first inclination is not to go and point out the limitations of it. And as well, marketing, if you were dealing with proprietary tools, that they're not going to want to go and tell you about the particular limitations that are involved. But that really feels more like an engineering ethics thing in a way, right? To be able to go and say, this is serious work, and we need to be able to go and articulate the places where this particular thing is not applicable. And if we don't do that, we're being not quite as responsible as we could be.
Yeah, I agree. It's just that I think there's a lot of gray areas where, this thing might be applicable if you do it this way, but maybe not. And there's so many gray areas that you can fall into, sort of boundary edge cases. It's really hard to be definitive. One thing I think we don't use enough, which is a fairly well-established body of knowledge, is metrics. We can fire tools at our code and we can measure stuff at runtime, so we can get real detailed feedback on what we're doing, what we're building, and how it behaves. And there's a whole body of metrics and really good tools now that work on a variety of languages that you can use to give you feedback on how your system's being built and where you should modify it and monitor its runtime behavior and adjust its performance or throughput, etc. So I think we should try and be a little bit more quantitative in our approaches and try and actually add numbers to things so we can talk in real concrete terms rather than, I don't like that class, it's too big, or that interface is too wide. Let's talk in numbers.
One thing I'd like to add to that, which I think is, I just love highlighting this because few people talk about it, is that with a lot of instrumentation, it's possible to go and discover in production where their code is just not being used, right? You'll never have a complete assurance. It's not like dead code analysis, but there are quite often paths in code that are just so infrequently used, it's really worth going and reconsidering within an organization whether they're even necessary to be there. And if we kind of look at systems as being not just this mechanical artifact that we produce, but kind of like alive in a way, it's kind of like a thing that can kind of grow as we add things to it, and we hardly ever do the thing of like removing things. And one thing that I just understand from a code level is that the degree of stuff, the amount of stuff that we look at that isn't being used is really kind of like a lie in a way. We end up going and having this very complex view of things which may not be as complex as we think, just because certain things are just never done. So I'd love to see way more metrics around going and allowing us to pare our systems down. Tools to help that.
That's a big thing in legacy, right? I mean, you inherit a legacy code base of 1 million lines, and you kind of wonder how much of it's useful to anyone.
So another thing we had going on, especially after seeing the presentations, is we're seeing a lot of history in architecture. I mean, architecture itself as a methodology or as a way of working is quite old. If you know, we have a lot of history of architecture in the programming history itself. So, is architecture like itself becoming more specific? Or I mean, let me give you an example. So we're working in the cloud environment, or some of us are working in the cloud environment. So is architecture more specific towards the cloud environment for us, or should it? What I want to say is, we have principles that are applicable to all the environments, and then specific principles that are for specific, and then for technologies, and then for versions, and then for people, for etc.
Okay, I'll take that one. I think it's back to where we were before. There are definitely, for me anyway, there are definitely principles which apply in many situations, and many different kinds of deployment environment, many different kinds of build technology. I mean, fundamentally, modularization, I think anyway, there are principles of modularization that would apply to assembler programs on mainframes, embedded programs in microcontrollers, and highly distributed systems running in the cloud. I think that's true. I think they all need interpreted, but I'm pretty sure that there are principles. For example, he was talking about highly distributed systems. They come with a whole lot of principles about how they work, what you should and shouldn't do, things that go wrong, which are not applicable, for example, to most embedded systems because they deliberately drive out that kind of concurrency because they just can't take the non-determinism.
Yeah, it's an interesting example I give is the way the world changes, and I think it'll continue to evolve. 20 years ago, maybe, I worked for IBM as a consultant, and we were building transaction processing systems using a technology called Transarc Encina. Ran on DCE, if any of you remember that archaic piece of complexity. And we were deploying these things typically for banks, and it was the late 90s. A lot of these systems weren't opened up to the internet. They were internal business systems. And what that enabled us to do is know how many users that system would have, because we knew how many machines there were in the bank. We knew how many people worked there. So we knew maximum load would be 3,000 users or something. So we could plan the capacity of our servers and our databases really accurately. And it made it reasonably straightforward to build these systems. But as soon as you open a system up to the interwebs, then your potential user base is, to all intents and purposes, infinite. And so this makes the capacity planning and your design requirements need to be much more flexible so you can handle spikes and bursts in traffic. And this drove over the last decade or so, at places like Google, Netflix, various other people, a lot of principles that we really didn't have 20 years ago. So a concrete one, we always used to measure mean response time for users within the bank systems. That's what we built systems to. Now you don't do that, because if you measure mean on an internet-based system, then that means that most people are getting a lot worse than that level of performance. So you have to measure the 99th percentile is now standard practice to track how you actually control your latencies. So this is one of the things that's been created over the last decade by us, the need to build much more scalable systems. And with this, there's a whole bunch of patterns. So I hope you've all read Michael Nygaard's Release It book, because it's just full of wisdom and patterns like the bulkhead pattern, the barrier pattern, all those kind of things, which are really valuable in building scalable systems. So I think the knowledge is evolving based on the demands of the systems that we're seeing.
I think architecture practice evolves quite a lot too, because again, I think this has come up elsewhere, but architecture knowledge and decision making used to be relatively centralized. A lot of it was more upfront, but then that was a different world, because we started with a compiler and an operating system. There were a lot of decisions needed to be made very early. They were hard to change later. Now we've got Also, we tended to deploy a thing. I mean, maybe 2 or 3 things, but certainly not 100 things. Now we've got a microservice-based world. We have DevOps practices and continuous delivery tooling, or continuous delivery tooling and DevOps practices, whichever way you like it. I mean, cloud allows us to get our infrastructure on demand. Our teams are agile. We've got a lot of parallel stuff going on together. Therefore, that way of architecture working is just doomed, because the architect, with the best will in the world, even if everyone's trying to cooperate, will simply become overwhelmed by questions, demands, complaints very, very quickly. So it has to become a very kind of shared responsibility, shared commons kind of a thing, which I think we're still feeling our way through that transition, actually. But that, I think, is the implications of some of what you're talking about in terms of the technologies we're now building within the demands we see on the systems.
So the topic of decomposing in modules has been mentioned several times, both today and yesterday. And so one of the original papers on this that I discovered, at least, is called "On the Criteria to be Used in Decomposing Systems into Modules." And the funny thing about this, it comes from 1971, right? So yes, David Parnas. So what I meant to say, or what I meant to ask is, so is our architecture really evolving? Are these like base patterns really evolving, or are we just rediscovering again and again?
One thing I think is kind of interesting one thing I'd love to see more of, and I maybe it happens in universities and I just don't really see it, is taking a novel architecture, a new technology applied in a particular architectural style, and taking these older principles and just saying, okay, here's an instance of where this reasoning was used, or this is an example of this kind of thing. And maybe I'm just kind of like not tied into those conversations to go and see where people are going in, taking this older knowledge and these named principles and saying, look, you can see it here, and you can see it here, and you can see it here. To the degree that we do that, I think that really goes and helps us go and develop more continuity of knowledge in this space. I just don't know whether that's happening.
Yeah, I don't see a lot of it in the limited university teaching and practice that I'm involved in. How about your course, Ian?
That's the academic. Yeah, so I mean, I teach a course called Building Scalable Distributed Systems, and we definitely do try and show how things have evolved. So a good example is messaging technology. If you look at the traditional Java messaging service type implementations, they're really good for doing certain things, but probably not at super high scale. That's when you need something like Kafka that gives you, replicated queues and subscriber groups and these very simple mechanisms, simple but incredibly powerful mechanisms to scale a messaging system. So yeah, I try and do that within my classes, give people context on why we've evolved into the state we have now. But yeah, I don't know if it's true of everybody.
We seem to keep rediscovering things roughly every, how long? 10 years? 15 years? I don't know. So my best example of that is, I don't know how many of you remember Steve Vinofsky. I think some people up here will. He was a kind of Corba guru back in, in fact, some of you probably haven't heard of Corba, which was roughly the same era as DCE, in fact. Yeah, so it was a distributed computing system, which was a kind of evolution of Sun RPC that you definitely won't remember. You're all too young. But Steve Vinofsky, I worked a lot on Corba. Steve Vinofsky was a great hero of mine. I met him some years later, having watched his writing for a bit, and we had this kind of slightly grumpy old men conversation where we kind of went, Sun RPC made a lot of mistakes that then we discovered again as we built Corba, and then everyone told us Corba was nonsense, and obviously we had to be much more open and flexible. So then the XML web services people, the WS star people, made all the same mistakes again and discovered them once again. And then everyone realized that that was flawed, so they are currently making all the same mistakes again with JSON over HTTP type REST web services. So I think this happens repeatedly, because I was also in database systems for a long time, and it really amused me, having learnt the hard way about things, the sort of things you were talking about concurrency, write-ahead logging, reliability transactions, to meet the world of NoSQL databases and discover, what do you know? These things are quite important. And it seemed to be a complete surprise to the NoSQL vendors that actually not losing data, transactionality and reliable replication was stuff that people might need. And again, it's just 15 years on, they just rediscovered it again.
Yeah, it's kind of amazing because just software development's been growing so much. I forget the numbers now, but how many new people enter the field every year?
Yeah.
And with that kind of scale, you end up having an incredible amount of fragmentation of knowledge. So there are a lot of things that are generational effects and fragmentation across the industry. I'm not sure we can expect it to be really better than it is right now with that. I guess the one thing that's kind of interesting about this is kind of a positive in a way, and it's like I guess you can look at this totally outside of the software development industry, but it seems like in the social world quite often, like every generation goes and learns, the things that basically they want. They kind of rebel against the previous generation. They end up learning the same lessons sometimes. But the thing is, you have to try things over and over again in order to go and discover maybe there's this niche area in which this particular thing works that all of your elders told you it really wouldn't work under any circumstance. So there's a benefit to going and actually redoing things, even failing sometimes.
Part of progress.
So if we have to, if every generation has to make the same mistakes and rediscover, when do we have time to evolve our architecture, our systems, our principles?
I think that's part of Michael's argument, is that by re-implementing and relearning, there's 10% innovation every time. So that's how we progress, is that?
Yeah, there's that. And there's also this issue that essentially a lot of this stuff does become durable, right? I mean, cohesion and coupling, people should understand and generally do, and we make progress with that. I think the thing that's really kind of great is that these days, it's like there's so much information out there. Anybody who just really has the curiosity to Google something can find, a wealth of material about these things. So it is discoverable.
So we've mentioned cohesion and coupling and modularity. What are other principles, in your opinion, that are fundamental to software architecture?
I'm just going to go and say Conway's law. I mean, I just harp on that all the time, right? And just from the point of view of I think it's just really something which is way bigger than what Mel Conway articulated, that there is interaction between many different things at an architectural level, at a social level within teams that people don't really think about all that often. Just to go and offer a very simple one, sometimes in organization and process, people go and make this case for having feature teams rather than component teams. If you have component teams, you can have siloed development and then end up having things that basically sort of grow off on their own without much interaction from other teams. And quality can degrade in that way. Then you have the other thing of having feature teams where people can go to any area of the system and make modifications. But with that, sometimes you end up having the tragedy of the commons, right? So it's kind of like this interesting thing of once you kind of understand that dynamic, then you can basically go ahead and sort of make decisions based upon what you want in particular areas of the code base. But understanding the dynamic comes first, and seeing that that's really an extension of Mel Conway's insight is kind of interesting to go and notice that the way that we structure ourselves and the way that we work does impact the quality of the actual character of the things that we produce, and vice versa.
Just for the record, can we have a quick refresher on what's the Conway's law?
Yeah, so Mel Conway basically made this observation in the late 1960s. He couldn't get it published right away because he didn't have any empirical evidence, but it's since been validated by a number of studies. What he basically said is that when teams design something, the thing that they produce ends up mirroring in structure the structure of the teams that produce it. The old joke with this was that if you created a 3-pass compiler, if you have 3 teams working together to create a compiler, it'll be a 3-pass compiler. And the reason behind this is that essentially, since there's a cost to communicating across teams, invariably it's easier for us to go and produce interfaces between the things that we produce in different teams. So our componentization tends to mirror the structure of the teams that we produce in an organization.
So is there any other fundamental principle that you would like to add to that list?
Systems that operate under reasonable loads, I think a fundamental principle is that you have to inject monitoring code into your system. Because if you don't know what's happening through looking at your monitoring code, you just have no clue about their dynamic behavior because it's so complex. So the general issue is called observability. You need observability into your system. And of course, this comes as an overhead. You have to capture events and somehow log them somewhere so that they can be processed and analyzed and give you insights into your system's behavior, so you can sort of analyze it in sort of data-driven ways. And one of the things I teach my students is that you really have to think super hard about how to make this monitoring and logging occur in the most lightweight way possible. But it's essential that it happens, because if you don't inject it, you just have no idea of what's happening half the time. So I think that's a general principle that we could all follow for building server-side code.
For me, I'm not sure I've got it very well thought through, but it's the fact that synchronous and asynchronous systems have really fundamentally different trade-offs about them, and they're both very attractive in different situations, but should you pick the wrong one, you're in for a lot of pain.
So if I'm up for a lot of pain, how do I make my system evolve and my architecture evolve painlessly, or as much as possible?
Experiment. You can, if you're unsure about a design decision, then build both, deploy them both, and watch what happens at runtime. Just split some traffic between the two and get some data so you know exactly what's happening. We're all subject to experiments by internet sites all the time. They're all doing these A/B tests, and they're doing that to validate design hypotheses. Does this work? Do they make more money out of it, or do the systems behave better under certain conditions if you deploy different features, different capabilities? So I think for many of us, the decisions are too complex to make up front. You've actually got to test them out at runtime. And to do that, you're digging into the world that Len was describing with DevOps about how to do these experiments at runtime and gather data and do an assessment of their validity.
For me, to evolve an architecture, I think there's two things. One is sounds obvious, but to change things regularly. One of the problems I've seen actually with some of our clients is that they think of development as something you do and then you stop. And at some point later, and then you go to what we call application management, which is a small change, and then you start again. And actually, that's very difficult. What we're trying to persuade clients is that we've got a phrase, we're not sure if it's ours or a general one, but we call it evergreen delivery. And what we mean is you just change things all the time. And you never go to development teams being completely shut. You're always changing something. But the other thing to allow that is to keep technical debt under control. Technical debt is something I thought I sort of knew about until about a year ago. I'm now getting much more interested in it again. It's a lot, this is obviously much more something Michael's an expert on than me, but it's a really interesting area, technical debt, and massively, sometimes oversimplified and sometimes overcomplicated. But I think keeping intellectual control over the technical debt in your system largely governs what options you'll have in the future, so that has a big effect on how evolvable your architecture is.
Yeah, I guess I'll just kind of echo the issue on technical debt. The thing I think is kind of interesting for a lot of us, technical debt was a metaphor that was first kind of like articulated by a guy named Ward Cunningham back in the US. And he basically sort of likened, the deterioration of systems to being something which you could kind of like quantify, like debt in financial systems. What I find fascinating about this is that it seems that metaphor isn't strictly necessary in order to go and actually do some work with it in nice ways. One thing that I've done with teams every once in a while, which I think is pretty valuable, is to go and actually sort of like say, look, let's build a simplified view of the system and color each component by its health, right? And then what happens is that whenever we're doing planning, it's just very visible how healthy particular areas of the system happen to be. And people can take this into account when they're basically choosing what features to go and deliver and stuff like this. When we see systems deteriorate over time, I think quite often in this world where we're doing continuous work, it's because we've not closed the feedback loop with the business. And so they ask for features, but they have no feedback about what's happening to the health of the system in terms of its changeability, its maintainability. It's easy to see that it's going to fall off the skids.
Yeah, I think that's really true. I've seen that on systems I've been asked to come in and work on that were already distressed. And you go and talk to the business about it. I mean real business people. I don't mean business analysts or product owners, people who actually are paying the money and are having their business crippled because they can't change the system. And you sort of break it to them that this is at least 50% your fault. And they're often surprisingly, one, surprised, but two, open to that idea, because when they think back, they say, yeah, we did push the team really hard. And I do remember now that there was some noise about this not being the right thing to do, but we did it anyway. And they go back sort of through their memories and realise that actually, yes, maybe we've got here together. It's quite a difficult conversation often.
Oh, it definitely is. And it gets back to what Ian was saying about like observability and metrics as well. It's like if you need to understand something in production and how it's behaving. We need to understand development, okay, from the business point of view about what are the quality effects on the system that we are actually working on, and we can.
Because we don't reflect that back in a way that business people understand. We just sort of grumble, which is not quite good enough.
So we had another topic here, and I'm thinking about the, related to the title of the panel discussion of the software architecture, and I was wondering, how do we make this evolution in our systems and in our architecture happen? How do we take an existing system, maybe legacy or maybe not?
They're all legacy.
Okay. They're all legacy, okay. So how do we take an existing system and we make it evolve? So I was thinking whether it could be modeled something close to natural selection, or whether human selection or artificial selection. What do you think about it?
Well, if you're dealing with things like natural selection and stuff like that, typically you're dealing with a population, of organisms, and some are going to survive and some aren't, right? So I think there's limitation in applying that metaphor to a single instanced software system. The thing that Ian was talking about earlier about going and running two different versions of things in parallel and saying, okay, let's go and see which one people like, and then we'll switch over. I haven't seen enough teams doing that sort of thing, but I've been hearing a lot more recently about, even having wildly different systems and running side by side and saying, you've got version A and you've got version B, which one do you like, or which one do we see people engage with more? But that often requires you to do some very, duplicative development, in order to go and actually run those experiments and do those kinds of things. But I think selection like that really only happens when you have a base of a couple of different things you can select from, right? So I think there are many aspects of the evolution of software that do have a biological flavor to them, but the natural selection thing, I think it requires more of a larger sample space.
So then we'll be talking about what kind of evolution of our systems.
I tend to think more about growth in systems, right? Just like as we add things, they grow and they grow and they grow. And I guess, getting back to this interesting thing we were talking about earlier with essential and accidental complexity, there's this interesting thing that systems are way more complex than they were in the past, and we can consider that essential complexity based upon what we're doing now with distribution and cloud and all these different things. So things become more and more complex. But the thing which is fascinating is that it's really the competitive landscape between companies which goes and accelerates, the complexity of the things that we are doing. We want to compete with, Amazon or like something in particular area, so we try to go and get those features growing as well. So we really are in a bit of a complexity treadmill right now. One of the things that I'm really kind of interested in, even though this is a little bit peripheral to architecture, is there's a new thing that's coming out called Darklang, okay, which is by Paul Biggers, and it's an attempt to radically simplify the tool chain to go and actually get to the point where developers are able to, as they type code, have it go into production for selected users, and kind of like eliminate the whole CI/CD pipeline by going and automating it away. And I'm not sure that that's the right answer, but I think it's really the right problem, because we have such an incredible amount of complexity in managing our infrastructure and our environments right now that we didn't have 20 years ago. And I'm waiting for the grand simplifications of some of these things. It's just going to get more complex unless we find ways to simplify these things.
I do think that's one of the things when I've observed really good architects working. Now I get the chance to observe people, but also when I was doing it, I do think that's one of the things that really good architects are good at, is radically simplifying things where they can be simplified. Obviously, there was always the principle of do the simplest thing possible. That's all very well, but what is the simplest thing possible? And actually, that's one of the things that good designers do really well. They spot where there's complexity there shouldn't be, and they're brave enough to step back and say, we don't need to do that. This needs to be simpler.
So regarding the simplicity and putting it back together with a growth model, so we have this way of thinking as software as a garden rather than as a building. Or can you talk a little bit more about this garden metaphor?
Yeah. In fact, I have this like rather atypical view of these things. I don't really think I like the term metaphor very much with this. Just from the point of view that I think that there are certain characteristics of things that change incrementally over time that lend these things to end up looking like biology. If you look at how cities grow, there's a very biological feel to the way that cities grow if they're not like this, planned suburb or something like that. So when you change things incrementally, it goes and gets this same kind of aesthetic quality in a way. So I think that that's really very much true of our work, and we don't really appreciate as much that that systems will start to sprawl, and whatever componentization or modularization that we produce, its tendencies for each of those pieces to grow rather than to break apart into separate pieces unless we intervene directly with those things. So I think understanding those kind of growth dynamics is pretty powerful. I guess you all know, like Layman's laws, I guess, how Layman's laws of program evolution, I think, is one of those things that is underappreciated within the context of a lot of the work that we do. And it's, again, one of those sets of things that's just from the past and probably hasn't been brought forward to this generation enough.
For the record, again, can we do a quick refresher on these laws?
It's actually like outside of my span right now. I'm a bit jet lagged also. But his name is, I think, Manny Lehman, Lehman. And it's just, he has a categorization of the complexity of different kinds of systems based upon their interaction with their environment and what you can expect from different types of systems. And then a bunch of different things about the growth of systems. But that's the thing that I think is kind of interesting, is this longitudinal view of systems. And sure, I'm the legacy code guy, but it's like all systems become legacy over time. And it's like to take this view of like from the moment of inception to when it's out, 30 years and outsourced to some other place and using tools that are 30 years old as well. There are characteristics to these systems that we can pay attention to.
Yeah, I confess I'm not very fond of the garden analogy. I have a garden, and it doesn't seem to be very like a software system.
It's prettier, right?
Yeah,
Prettier?
much more attractive. Yeah, at least in the summer. I think it's a funny thing about the software industry. I've worked in a couple of industries, technical industries. I've not been in another industry that is so desperate to find its ways of working in a different industry. I mean, medics don't do this. Medics don't say, we should be more like civil engineers or whatever. And civil engineers don't say, well, actually, funnily enough, they are saying we should be more like software engineers, but that's about agility. But, I mean, they don't say we should be more like evolutionary biologists. So I'm not quite sure why we keep doing it to ourselves, but I think all of these analogies have some value in that there's probably a kernel of truth in them. But the mistake I see people make repeatedly is to take them a bit too seriously. There is no scientific basis to any of them. So if they help you think about something, brilliant. But just bear in mind, as soon as it doesn't seem to fit, it probably doesn't fit.
Yeah, the analogy one's always a fun one. I really hate the analogy of architecture to buildings, and the reason is as follows. Software is this amorphous thing that you can't kind of touch and feel. So people, make assumptions about it. And the way I kind of make that concrete is, think of the Sydney Harbour Bridge. It's a big bridge built in 1932 or something. And it soon reached capacity. And you really would want like another bridge or more capacity to get over the harbour. But it's almost like in the software world, someone say, okay, we need more capacity, do this. In the physical world, the analogy is, okay, well, can you just move that bridge a bit down the river and add 20 lanes to it? And no, you can't. You can't because it's physical and you can see it. But in software, people ask us to do those kind of things all the time. And it's just insane. As an architect, you've got to push back on these sort of misguided notions that just because software is sort of infinitely malleable, you can always change it to achieve something. It may cost so much to actually change it, or it may be so hard to make it reliable once you've changed it. It's just not worth the effort. You've got to make something different. Just because people can't touch it and feel it. It's a really tricky one.
So to give you a counter argument to that, we always say that software should be soft. For hard software, we hardware, right? So how do we find the balance between softness in software and...
This is why I always go back to quantification and measures, because it's the only way we can attempt to sort of give people concrete insights into the complexity of what we're building, whether it's structural through sort of modularity metrics or behavioral through performance and latency metrics. And then you can at least have a sensible discussion about what your system's capable of. And if someone says we want to scale it 100 times in the next 3 months, you might be able to say, okay, this is going to be challenging because of this, this, and this, and here's the numbers to back it up. But if you don't have those numbers, then you just get into these endless arguments about what's possible and what isn't. And so numbers make these discussions much easier.
Yeah, I think it's a worthwhile thing looking into, but I think there's this other thing, I guess another analogy, I guess in a way, is organizational change. Somebody I really respect in the industry basically told me years ago, it's like when you're in a big company, you can't change anything in less than 6 months, and quite often changes take up to 2 years. And it really comes down, I think people are way softer than software in a way, right? But we have our own inertia to the way that we work and acclimation to going and doing new work practices and stuff along those lines. So, maybe measurement in that case is kind of like, okay, case study. It's like, okay, implementing these changes in this corporation, it took this amount of time, this is kind of what you can expect. And the same thing with, I guess, scalability and things like that in systems, developing more of a feel for it. But of course, every system's going to be a bit different. These are all just probably going to be rules of thumb, I guess.
I think one of the things we don't do very well in our industry is apply what we're doing for our clients to ourselves. It's a kind of cobbler's children thing. If you think about automation, it's now very trendy to be into automation. The first COBOL programs that were written in the 50s were automating. They were just automating business systems. But we didn't automate anything about the software process. It took Dave Farley and Tess Humboldt to kind of write a book where we all kind of went, oh yeah, we're really rubbish at this, aren't we? And there's been this, explosion in automation for the deployment pipeline, which is, fantastic. Thank you, Dave. And it's made a huge difference to the industry. Well, it's still a process we're going through, obviously. But I do think, I sometimes look at some of the stuff we do in data and analytics for business data. In fact, we are starting to experiment with this a bit in-house on code bases. I think, and there's decades of research into mining software code bases and getting what you might call business intelligence actually out of them. And yeah, I hardly see anyone using automation beyond the stuff that's, like to production, and also using, as you say, being data-driven in software. I'm as bad as anyone, so I could criticize myself on this, but it does seem that we're somehow missing a trick there.
Yeah, and one thing to point to, there's a guy named Adam Tornhill who basically does does conference talks, and has a couple books out, and he does a lot of repository analysis, and it's kind of funny because quite often when we do this sort of thing, it's basically to give the business feedback about the business, but like as you're saying, giving ourselves feedback about like what have we done in the past and what trends can we see in code bases and architecture.
Yeah. So we're running out of time. I'm sorry for that. I would like to thank you very much for your time and for your answers. They're really cool. I learned a fair bit today, and there's a little bit more learning to come. So I would like to thank you very much for this, and we'll see you around.
Thank you.
Thanks a lot.